This video will begin our discussion of cylindrical coordinates. We're going to end up integrating over this, so let's discuss what the system is. This system is just an extension of polar. Remember, polar is, we had two points. We would have r, and then we'd have theta. And r was, let's look at this picture over here. R would be some radius, right, that we'd have, and then theta would turn it over, giving me a point out here. Right, the r is the radius, theta is our how much is it turning, and then to extend it, all they did is add a z coordinate. It's nice and pretty. The z is exactly, if z is 5, it just goes up 5. So that is the cylindrical system. We can create rectangles as well through here. I'm not going to go through some crazy, the book, if you'd like to look at the curriculum, like in these other sections, will drag you all the way through this of how it's built. I'm not going to do that because most of the time my students will glaze over. I will leave that for your advanced calc classes if they get that far. So here's our top right. That is our how we would build rectangles here. And then we could actually find the volume of each block, right? And they give us each dynamic length times width times height there. I'll let you check that out and how that's built. We also, we've talked about this before. When we see something like this, what that means is that it is taking each coordinate. This is where the x was, so that's what x will be. They took y, that's what y will be, and that's what z will be. That's what's written right here. So that is just shorthand to say, hey, convert your function into these terms. All right, so this little thing here, this again comes back from like polar where this r happens. That r is still going to happen. So this is what it's going to look like. We're going to have some integral of theta, some integral of r, and some integral of z. All right, and then we're going to have the whatever function was here in terms of what we wrote down. So change x to that, change y to that, and then leave z as z. And then we're going to do times r, that's that polar thing, it's still here, dz dr d theta. So all it is adding that z dynamic. It's just like polar, it's just we're going to have a z now at that very end, and that will be our surface. All right, so let's try an example. We have this integral. We're not exactly finding volume, so I don't want you to think that. We potentially could be, just depends on how the problem is set up. This one is just an integral. So here's our integral over a section of the surface negative 2x, but they want over the bound, over the region T. All right, so T is the solid bound by, okay, we have that surface in the first octant. Yours should be typed there. In the first octant. So if it's in the first octant, we are kept by the xy plane and everything is positive. So I'm going to, I'll show you how I got this circle here. Z equals 0 would be the xy plane. That's what's going to be projected there. If I set this equal to 0, and I add 9, let's leave 9 there and add the other stuff over. Equals 9. I divide out this 2. Equals 9. And then I got x squared plus y squared equals 9 over 2. But I'm going to use my conversions because that's what we're going to be using here. X squared plus y squared is r squared, which is 9 over 2, which tells me that r is 3 over the square root of 2. That's where we got our circle above there. That's what's projected down onto our axis. So let's write our bounds here. We got z caught between. Then we're going to have r caught between, and then we're going to have theta caught between. Now, since it's in the first octant, our circle's only shaded up there. Octant, remember, is the first quadrant, but extended up into 3 dimensions to get a positive z. So I have r. R is caught, right? If I look at my picture, the origin starts in the region, and it's consistent all the way through. So I know r is always between 0 and 3 over radical 2. The z, I know, is caught between the xy plane and the actual surface itself. Well, the surface is going to be, 9 minus, it's this function here. Let's take this function. Z equals 9 minus, and then let's factor out that 2. And you can see that you can replace x squared plus y squared with r squared. So I know z is bounded above by 9 minus 2r squared and bounded below by the xy plane. All right, so that just came from here. That's the surface that we're dealing with, and we want above, that's above, but we want to change it to r, so we replaced x squared plus y squared with r squared. Now the last thing we have to do is theta. That is what this projection over here is useful for. I can see the angle. It's between 0 and pi over 2. All right, let's set up our integral now. Cool. All right, so we have theta's between 0 and pi over 2. We have r is between 0 and 3 over radical 2. And then the last thing, z, is caught between 0 and 9 minus 2r squared. I have to fix this one. Doesn't have a 1. It has this in it. So I'm going to replace it with negative 2r. It's x, so it's going to be cosine theta. And then times r dz dr d theta. To save time, I'm not going to work this integral out. This one's actually pretty straightforward if you'd like to give it a shot. If I work this out, this is equal to 81 over 16 pi. So again, setup's very important. Setup's the most difficult part, especially with these conversions. The thing I see most here is just like polar. People forget that. Most of the time, I think usually these problems are very easy to set up once you get past this whole point and you draw a picture and you can see it. Because once you draw a picture, these two just become evident. You can look at the picture and decide how much does it move with theta, the angle, and then you can look at it and determine your r. The r sometimes is not as straightforward, but those are the most difficult parts. Typically z is easy to find. It's just converting it, and then they usually stay with the xy plane, or they'll give you a surface underneath to bound it with.